At this point, we've looked at collisions in one dimension. So hopefully you're pretty comfortable now with conservation of momentum problems when it's in one dimension. When we have a collision, we can find the momentum by adding the momenta of the objects before the collision. You take your mass times velocity, then you add them together, and then the momentum before the collision will be equal to the momentum of the objects after the collision. If we start looking at two-dimensional systems, we can separate the motion in the x direction and the y direction, and then treat them individually. The momentum in the x direction is conserved, so you can add up the total momentum in the x direction before the collision, and it will be equal to the momentum in the x direction after the collision. Also, the momentum in the y direction will be conserved, with the total momentum in the y direction being equal to the momentum in the y direction after the collision. So the good news here is you can do exactly what you did before with one-dimensional collisions, but now we're treating the x and y directions separately. To give an example of this, we have a completely inelastic collision between two cars here, and we want to solve for the direction that the combined cars after the collision travels. So in this case, we have two cars. Car 1 is heading east, and car 2 is heading north. When the two cars collide, we want to find the direction that they travel after they have collided. So first, we want to find the velocity along the x direction. The initial momentum in the x direction is all due to car 1 because car 2 is heading north. So initially, car 2 has no momentum in the x direction. So the momentum in the x direction is equal to the mass of car 1 times its initial velocity of car 1. The final momentum in the x direction will equal to the momentum of car 1, and it will also be equal to the sum of the mass of car 1 and car 2 times the final velocity in the x direction. So the x component of the velocity will be the mass of car 1 times the initial velocity of car 1 divided by the sum of the two masses. Next, we do the same thing to find the y component of the velocity. Now, all the momentum in the y direction is equal to the mass of car 2 that is traveling north times its velocity. To find the y component of the velocity, we will divide the initial momentum in the y direction, the mass of car 2, times the initial velocity of car 2, divided by the sum of the two masses. So if we want to find the direction that the car is going, we can then find the angle that the car are traveling at by taking the inverse tangent of the y component of the velocity divided by the x component of the velocity. So it should make sense that if car 2 is either much more massive or traveling at a larger speed, then the resulting collision will move in a direction closer to north, while if car 1 is going faster or is more massive, so it has more momentum, then the collision will be closer to traveling east. Okay, so now you have a question to do, and so this is looking at the collision between two hockey pucks in 2 dimensions. The question will ask you about the change in momentum. Remember, the momentum is a vector, so when you look at the change in the momentum, you will take the final momentum and subtract the initial momentum. It's just that it's a vector, so you're doing vector subtraction. Okay, so that's it for our unit on momentum. I think for the next class, we're going to do a wrap-up of our work on linear motion, so with a review of free body diagrams and a look at inclined planes. All right, good luck and take care of yourselves.